Hello, everyone. Thank you for joining this call. Thank you, OCP, for setting it up again. I know a lot of people have worked in the background to make it happen, from the physical to the virtual. So thank you. My name is Venkat Pulela. I'm a distinguished engineer at Broadcom. Today, we're talking about designing efficient programmable switching pipelines. Let's jump right into it. So this is our agenda. I will start by talking about programmable architectures compared to the fixed function ASICs that we are used to. And then while we are designing these programmable architectures, how do we make an efficient design? What are the dimensions we need to think through to make the designs very efficient? And then in the end, I'll summarize the design decisions and then what we can do about this programmability in the OCP projects. I'll end with that. So what is a programmable pipeline, right? When we go to a programmable architecture, what changes, right? So here you can see that instead of taking a fixed field, right, could be just a Mac VLAN, you could pick up from a selection of fields, right? Could be any field on the bus. And then that field, that input flexible key is being fed into the table. So depending on if you pick up layer 2 fields, the table becomes layer 2. If you pick up layer 3 fields, the table becomes layer 3. So that's the whole idea of programmability. And same thing, once the result comes out on the output side, you can decide to update the layer 2 result or layer 3 result, or it could be fields. There could be layer 2 plus 3 plus 4 also in parallel. So you could do hybrid things of that sort. One more thing to point out is something called flex code, which is different from microcode, which is fetch an instruction execute model versus it's kind of setting up the path. Your high-level languages like NPL or P4 are programmed. You describe your pipeline requirement in either NPL or in P4 or other language of your choice. You compile it. The output comes and programs this flex code. In a way, the program is deciding what fields are going into this table and what the table does. So that's a programmability. One note before we continue, though, is there's a lot of talk, you see about, programmability doesn't have any extra cost. No, programmability has extra cost. As you can see, just to make a flexible table, see the number of fields. There are additional wires being run to select the input, select the where the results go out. There is a mux and a demux. There is flex code. So it is costly. It is not free. And it's very important to build a very efficient design. If you don't make it efficient, what will happen is that, yes, you can give a lot of good demos, but when you write these programs, compile and try to fit it in the hardware, they don't fit. And that's the problems you see, with a lot of architectures, okay? Let's jump into the 2 or 3 standard architectures you see in the industry. This is maybe familiar to you from P4. It's called PISA. It's a protocol independent switch architecture. Just like the model we talked before, there's an ingress pipeline, buffers, and egress. A couple of characteristics of this is you see these stages that are cookie cutter type. They're all same size, same amount of resource allocation. That's one aspect of this pipeline. The second one you see is something called match action tables. We'll get into. So each of these stages have multiple of a table, a lookup, and then followed by an action, basically. So there's a match and an action, an array of them in each stage, and there are many stages like that. So it's a uniform pattern that repeats everywhere. The other thing is also that you see that it's the same universal primitive. There's a match action table as a universal primitive. Whatever functionality you need to get out of that primitive. So everything is mapped into one universal primitive, and that is the building block for all the functionality of this kind of architecture. So another architecture that's fairly popular is again used by Broadcom in Jericho 2 ASIC from Broadcom is something called a sidecar architecture. There is a pipeline which has the usual basic functionality. And then from the standard pipeline, you can go off and do some additional functionality and come back to the pipeline and continue. And then these are the flexible elements called programmable element metrics you can see. So after this lookup, you can come out and do additional process and go back. And these are all programmable elements. So this is something that you could change and add your own custom logic. The other architecture is a tiled architecture. I call it a Lego block architecture. It's as if the pipeline is made out of these Lego blocks. You can select a bunch of blocks and put them together in parallel as well as serial. A couple of things about it is a non-uniform resource allocation. You can see that at each stage you are doing different kinds of blocks as well as different number of blocks. And what are these blocks, right? It could be a TCAM table, it could be an index table, it could be a fixed function, it could be like a checksum or a ECMP computation and things like that, right? Or it could be a parser. So you could have multiple parsers here along the stages. So multi-stage reentrant parsing is one of the unique characteristics of this architecture. Multiple, and then anything you see one below another, these blocks that are kind of kept vertically, they're all executed in parallel. So it's a very good architecture for doing things in parallel as well as building a serialized pipeline. Few things, and then we will get into the detail on how this kind of a disaggregated architecture and what are the efficiencies that you get out of this kind of architecture. So efficiency. So we'll get into the efficiency part of the pipeline and the switching design. There are many dimensions to consider. I took out few areas that are the top of the mind. There's a lot more things that go into these. So I do want to set a context to this. So while I'm talking about it, I try to kind of abstract out certain concepts and talk as high level as possible. I will show some examples, but they're going to be high level. But I want you to know the context behind it. So where I am getting all this data is from, at the time of this recording, it is still the world's fastest Ethernet switch, is a Tomahawk 4, 7 nanometer, 23 billion gates. With that number, you think you have a lot of gates to waste. You will see that how efficiency is really, is built into the design to make use of every gate at that level, and then it's very hard when you want to push some 25.6 terabits of throughput. You really have to optimize every inch of it. So you will see, and what are those dimensions, right? I try to abstract from it, but I want you to be aware that it's kind of the ideas are pulled out of the context of one of the fastest ASIC that we have. Okay, let's get started, right? So on throughput, how do we push lots and lots of packets through a pipeline? Intuitively, right, you want lightweight processing stages. If you have these big bulky things, and then as it's of course you can't push enough of those packets, right? And what are the building blocks of a pipeline? When you look at a pipeline, like we talked about, there are these match action tables, and then maybe some kind of logic, right? When you look at it, those match action tables are really bulky. They are too much functionality in one block. So when you get a match action table, if you are going with a PISA architecture, you can see that the blocks become very bulky and kind of becomes detrimental to pushing a lot of functionality. So one of the main design criteria to get the throughput high on the Lego block architecture or the tiled architecture is, first thing what we did is to disaggregate this, right? So what is consisting of this match action? What are the primitives, right? Can we make them into smaller primitives and build what you want, then use the match action? What if I want to do only match and I don't want action? Can I just do that, right? If you do that, it becomes a lookup, right? And maybe result, right? Lookup is your traditional lookup, fields in, fields out. What is the result? Result is a little more than a fields, right? As you go, we'll talk about it. It's a result object. You can associate a priority with the field. There is a width of the field. So instead of looking at it as a simple field, we associate additional attributes, and it's a rich object, and we'll get into that. Okay, and then it also feeds into how these fields are not just for data processing; it's for also doing decision making. So you need additional details about it. Process is about different kinds of results. What if IPv4 result is smaller, IPv6 result is longer? How do you kind of do some processing? What if you have multiple lookups of the same database? How do you process the logic? How do you process these results differently and things like that? So there is a unique concept called processing of the results before you go into action. Action, I think, is the easiest to convince that it's completely unique and separate from something called lookup. And combining these two, we'll get into a bigger, bulkier blocks and will affect throughput. Action is what you want to do with the results that you have produced through lookups. And we'll have some examples of that as we go. Then getting on to capacity, right? What is capacity? It's not just capability of the silicon, right? What is the capacity? How big is your layer 2 table? How big is your layer 3 table? What if I support only a single lookup table? That means we have a table I can look up only once. Then if you want to look up source MAC and destination MAC, you need to keep two copies of it. You make 2 copies of it, who will maintain them in synchronization? There'll be, if your software does it, race conditions, right? What happens while one is updated while the other one is not updated? So these single lookup architectures are not efficient and again have problems. And also for the sake of capacity, if we reuse the table, it's going to be very useful. So the first example I'm showing here is, a small little bit of pseudocode here. This is NPL, but I'm calling it pseudocode because it's kind of completely trimmed out. There is the same table called Mac table is being looked up as lookup 0, lookup 1. I trimmed a lot of things here just to give you a thing, kind of give an overview. So you could be looking up source Mac for learning and destination Mac for forwarding from the same table. And that will cut down the total memory usage into half. And for that, you need multi-lookup tables supported. There are many kinds of tables, not just match action tables. And then the more of these kinds of tables are supported through a tiled architecture, you could use the right table for the right functionality that you are looking, and that makes the whole thing very efficient. The other thing we talked already a little bit about resources, right? When you look at a pipeline, do you see the pipeline completely as uniform? Do you think when you are solving a big problem and you are making into small pieces, you need uniform resources across? Maybe you need some in the beginning, then you maybe need more, some less and more, right? So this is where, right, maybe we can learn, forget the machine learning, we can learn a lot from the pipeline designers who have been designing pipelines for decades sometimes, right? So when you talk to a pipeline designer, they would tell you that in the beginning, they are doing some lookups, like, let's say they look up based on the port, they want to figure out which is the VLAN, whether it is trunking is enabled, whether the packets are tagged, maybe there is a queue in queue, and things like that, right? So, and then that requires certain amounts of resources. If you over provision the resources, they'll get wasted. Then you get into another phase where they are doing a lot of computation, a lot of data processing, a lot of fields in, fields out, a lot of metadata is getting generated. Maybe after that, maybe you may make some decision making on if multicast, if IPv6, what do I do, things like that, right? So it's very typical of a pipeline being non-uniform, it kind of resources, and what happens at each stage of the pipeline is little more or little less, and it can never be exactly equal. You can always try to make it efficient by running some software algorithms, but dependencies do not allow that. So looking back at the architectures, 2 or 3 architectures we talked about, right? So looking for the right sizing resource architecture that gives you the right kind of resource at the right location in the pipeline becomes more efficient. If not, you will have a lot of resources, you get wasted. You have 10 match action tables, you're able to use only 2 other 2, 8 gets wasted, or you're doing only match and not using action, that also gets wasted. So right sizing the resources at the right locations in pipeline is very important for your overall capacity of these features and the number of features that you can fit into these ASICs, right? Programmable ASICs. And there's another concept I want to touch upon here is, again, logic versus tables. Is it really a choice? Is it one versus another, right? If you look at everything as a match action table as a universal primitive, it has a problem, right? When you disaggregate, you may have more tables and and then less logic in certain programs you may have lots of logic. So again, resources, what kinds of resources, where they are in the pipeline becomes very important. Otherwise, you'll have match action tables with match being wasted or action being wasted, okay? So moving on, a quick example of a logical table. This is an NPL program. On the left, you see a logical table with some characteristics and the key fields. And then there are 2 key methods that you can override, something called key constructs and a field assign. So here I'm showing, like we talked about, if I have a common layer 2 table, can I use a destination MAC and do a lookup 0 and a source address and use another lookup? And because you are looking up 2 different fields, can I interpret the results differently? One is for learning, another is for forwarding, right? So I'm interpreting the output, the port, as well as the discard bit differently for the lookup 0 as well as lookup 4. So NPL as a language, and then multi-lookup tables built into the architecture makes it very efficient. This is a good example. Going on to other dimensions, right? Concurrency. You want everything to be parallel. The more parallel you do, the earlier you finish, your latency is less and then more efficient. The more you do serially, you need bus. Bus, again, by the way, is a very costly resource. People don't quite realize how costly it is, right? Unless you are an ASIC designer. from sometimes theoretical point of view or from an academic point of view, just draw these lines and do some computation and say programmability is not zero cost. Oh, bus is free, the wires are free. These are not. These things come up with huge cost, especially when you are building an industrial strength 25.6 terabits per second kind of architectures. They really are on the cutting edge, and you really have to be extremely efficient. Here I'm showing an example. Is a very trimmed down example. Is nothing from a real life example. Imagine you are doing a layer 2 and a layer 3 and ACL in your own custom program. Let us say switching pipeline. Layer 2 might produce a port where the packet needs to go out on. Layer 3 might produce another port, and ACL might say drop and permit, right? So when you have this kind of thing, can I do this in parallel? Traditionally, these were serial. If you want to do in parallel 2 or 3 things, 2 or 3 features, each produce port. Each of them are telling you to go to a different port. How do you resolve this? This is basically, there is a dependency. See, what we have in some of this flexible architecture is something called strength. Strength is, in its simplest form, you can look at it as a priority. But like we talked about, instead of using a simple field, it's a result object. The result object has the field as well as strength. So imagine every field being an object. Every object has its associated strength. And then people, every lookup or every table is producing different objects. And naturally, these objects are resolving themselves. If 3 features produce the same port object, they naturally resolve among themselves using the strength construct and produce single port. So whichever has higher priority. For example, here, if the result ACL produces a drop result, the strength of 10 forces the packet to be dropped, and the port associated with that highest priority is chosen, right? So objects, and then fundamentally looking at switching pipelines as not just data processing, but also as a result processing, or as a concept. It is also a decision-making engine. Right. So if the pipeline is looked at as a decision-making engine, then this priority, as well as designing additional hardware construct like strength, allows you to parallelize lots and lots of features and improves all your the latency and every other dimension of efficiency we're talking about here. Let us go to low latency. How do we get low latency? To start with, disaggregate your primitives. That way, if you have a bulky primitive, only part is getting used, it should not, the other things should not slow it down. So disaggregation, like we talked about, disaggregation of match action table. Drive parallelism using strength primitives, like we just talked about, and then converting your fields into result objects with priority. Use priority across and look at the pipeline as a decision-making engine. Allows you to kind of take decisions and then parallelize multiple lookups, and that will allow you to kind of do more and more features in parallel. And then the more features get executed in parallel, less is the latency. And then, like I said, hardware constructs, if you do, versus you can do it also by using serialized, sometimes serialized processing of some parts of this parallelism, right? Some things that are non-obvious. Hardware constructs will help you. And then I want to close at least the low latency with something called speculative lookups. If you have match action tables, what does it mean? It means when you match, you also take an action. What if I don't want to take an action? What if I don't, because I'm not sure? What if I want to look at 2 tables, and based on the results of the 2 tables, then I want to take certain action, right? You want to speculative lookup, or sometimes to speed up. If you have an if then else, right? You want to take one path versus another path while that decision is being made. What if I could independently take these lookups and do speculative lookups, right? So disaggregation helps. If you have match action table, the moment you look up, you also end up doing action, then you won't be able to undo action, or that will become inefficient. So in that sense, speculative lookups also will help you parallelize more and increase your latency. Okay. And visibility. So this is one area people sometimes are confusing. Why is visibility? Yeah, I need visibility, but why is it an efficiency issue, right? It's a very important efficiency issue because the number of primitives. If you look at the tiles that we talked, tiled architecture we talked about, right? If you have to take a match action table as a universal primitive and apply on every problem that you have, and that as a single solution for everything, versus imagine you have a lot of these tiles that are flexible. So that way you can kind of construct the right kind of visibility at the right locations in your pipelines, right? And there are multiple things like trace points, probes, atomic snapshots, counters. Counters is a huge area. We can talk all day about it and still we won't be done. Maybe multiple days and still won't be done. So I won't go into the details, but imagine there are certain primitives, certain Lego blocks, certain tiles that are built into the pipeline. And by doing it, the pipeline becomes efficient, as well as you can do an efficient end-to-end design. Here I'm showing a quick example. Imagine a source machine talking to another destination machine, and there are parallel paths, multiple paths, and multiple routers in between. Imagine there is a probe packet that the source sends and goes from source and uses a path, goes to the destination. But while going, it triggers something. It triggers a user-defined condition. Then immediately all the counters and every other rich metadata is being collected by all the traffic that is flowing through. Basically, time zero, the first probe packet went through. And after some time, now you want to freeze and figure out what happened between time zero and time one. You send another trigger packet. It's again atomic in the sense that anything before the packet and after the packet are separated. A snapshot of all the counters and all the information and the data is captured and kept aside. And this kind of functionality built in a priori, not post facto, will really help make the pipeline be very efficient. And you'll be able to put more and more functionality into the hardware because of it. So like I said, we can go into the details of all these things. There's a lot of functionality here. We quickly went over, but maybe there is another presentation we can talk about that. Runtime. This is, so far we talked about one kind of efficiency, which is more pipeline efficiency. Runtime is more about your day, not the day zero, day one, day two kind of issues, right? Imagine you have a pipeline and you have a running network. You want to change something. How efficient is it? Do you have to go back and completely recompile your code and download and replace the whole pipeline? Or are you able to do dynamically changes, right? So whole programming languages and compilers and compiler-driven flexible and programmable architectures is one thing. And this whole runtime in itself is equally complicated, complex, and comes with rich functionality for all the pain, for the complexity that we take. Right? It comes with a lot of rich functionality. And this is very useful for, imagine a service provider deploying a new feature without completely re-architecting and redesigning their own, their network, right? You can also see a lot of value on the enterprise and data centers too, right? Not to downplay that. So what are we talking about? Here I'm showing an example. We talked about strength. There are priorities associated with different features. What if you want to reprioritize the features, right? So this kind of design upfront runtime, saying, there is a strength profile table here I'm showing, where at runtime you can reprioritize at the object level, at the feature level. You have a very fine-grained entry level reprioritization at a gross level, at a feature level, as well as system level reprioritization built into it. So such built-in reprioritization makes the whole thing very efficient in terms of use in the field, right? And few more efficiencies on that. While we are at it, right? At runtime, imagine fixed functionality. While we talk about fully programmable, there are times where you want, let's say you have a checksum. You're better off hard coding the whole thing and creating that. Yeah, you keep a flexible checksum also, but hard code that. But is there anything else around it? At runtime, can I change the inputs? At runtime, can I change the outputs? Does it support multiple modes? All these things are runtime functionality. So the tremendous amount of runtime functionality that can go into the, like for example, Trident 4, and that will give you a lot of value, and it makes it your day-to-day operations extremely efficient. It's not the pipeline and packet processing efficiency, but day-to-day use of it. And one good example is a dynamic table, right? There are 10 or 15 things I can talk about, but let me take a table as a most commonly used primitive as an example. If you have a pipeline, you have 10 tables on the input, 20 tables on the output, you're doing something. What if you want to take a new table and you want to insert? And this new table is this new feature or a new functionality you want to deploy, right? So such things can be done. So runtime has a completely parallel field, completely highly functional, has a lot of usefulness to it, and gives you a lot of efficiency when you're running the networks. Simplicity. Again, efficiency comes from simplicity. Like if you are a follower of the so-called KISS principle, right? When you have primitives that are natural and then map directly to what you do intuitively. As a programmer, as a designer, let's say you're designing a network or designing a pipeline for 10, 15 years. You are using buses and your overlays. So you are taking IPv4 and IPv6 and overlaying over each other, because you don't design a bit processing engine, you design a bucket processing engine, typically 8-bit, 16-bit, 32-bit buckets. Now, how do you map your fields that you have onto these buckets efficiently? Requires overlays. So if your languages don't have overlays, they not only it becomes very inefficient, because if you pick up a field from one place and field from somewhere else, then you end up with two buckets. Whereas if they are kind of managed and kept next to each other, and you have constructs like overlays helping you with that, then efficiently you are able to use one bucket and you have another bucket, and you can left out to be used for other features and things like that. So taking primitives that are really close to what power users use, and mapping them into your language and creating that simplicity is really efficient. And then one of the biggest examples of that is function logic. We talked about logic as a first-class citizen, right? When you look at pipelines, if you only have match action tables, or if you want you to look at it as only tables like the open flow, but world has moved on, and then you cannot get enough functionality out of those open flow tables, because you look at it only as tables and ignored all the switching logic. Switching logic is a substantial part of pipeline. So what if I'm showing an example of a logic function that is deciding whether you are doing layer 3 or not, and imagine 1,000 lines of it. People who have not considered logic as a first-class citizen, used only match action tables, are unable to fit lots and lots of this functionality and lot of features at the same time. Whereas because logic and switching logic is naturally one of the primitives, and the simplicity of taking those primitives and directly allowing programmers through the programming language makes it very efficient. Skipping over in the interest of time all the design decisions that are taken and to build a pipeline. I have covered some of them, others we can talk some other day. And then call to action. Once you have this fully programmable, we can go build in two relevant projects at OCP. Both Sai can leverage this open programmable efficient pipelines, and then Sonic, which is again a container-based operating system, can highly useful for when you have different requirements. You can take things out, put things in. It maps again very well with the dynamic runtime programmability we talked about, as well as programmable pipelines. Both of them can leverage some of the concepts we are talking about. Thank you for listening. Hopefully we have some more time for a couple of questions.